thanks for having us. We're really excited to get out and talk about RISC-V and what we're doing. Yeah, okay. So first I want to talk about the team here. So we are all from Seattle. We've known each other for about 20 years. We met as part of this like hacking collective when most of us were in our like early 20s, just out of school. We used to have this bank vault underneath the Wells Fargo in Seattle where we had like an old school hacker space. This is our third startup or fourth, depending on which subset of the founders you're including. Jeremy's our co-founder over here, who'll be talking in a bit, started a decentralized wireless or permissionless wireless mesh networking startup about 20 years ago. Me and a couple other people from this company worked there. After that, Jeremy and Frank went off and did GPU accelerated bioinformatics. And then after that, all of us together did a startup called Vertex AI. We made this little open source project here called PlatML, which is a tensor compiler for making AI algorithms work more readily across a broad variety of hardware. So that company was eventually acquired by Intel. We ended up at Intel for 3 years, and Jeremy here does math papers to go to bed. So he's been into ZK for a long time. And we started talking about this, in earnest about a year ago and started the company in, I guess, October, but really earnestly got working on it in November. But like a good bit of the groundwork was laid by then. Okay, so today we're going to be talking about RISC-V. It's a general purpose ZKVM. We're going to be talking about a couple different aspects of this, but fundamentally, the purpose of RISC-V, our company, and this technology is to really bring verifiable computing in the form of ZK computing to a much broader audience through enabling, it to look like a computer that most people are used to interacting with. Okay, so when we say ZKVM, maybe this is obvious to some people, but what exactly do we mean? So it's not direct to ZK. You're not actually writing a circuit. You're not optimizing particular arithmetic gates or anything like that, like you might have with Alio or using CIRCOM or anything like that. Instead, your circuit is in fact a VM. It's a circuit that describes a microarchitecture, so similar to Cairo or Miden, if you're familiar with that. People are also making ZK EVMs. There are obviously different approaches to that. Generally speaking, people are either directly trying to interpret EVM bytecode or making their own sort of more RISC EVM code to lower EVM bytecode into. And then we're obviously doing RISC-V as a ZKVM. So what does that look like? The ZK circuit itself is actually an implementation of the RISC-V 32-bit immediate mode, something like this, integer, whatever.
RISC-V 32 IM or whatever.
Yeah, right. It's one specific subset of the current RISC-V specification. So the way you program this looks a lot more like a traditional computing system. You have your libraries in C++ or Rust. Those are currently the two languages we support, although eventually, in theory, any language is supportable. It's just a tool chain issue, and it takes some number of days to weeks to get new languages working, I guess. Probably we support a bunch more languages that we don't even know about at this point. But yeah, so anything that really targets LLVM, IR, or GCC really gets turned into a traditional ELF file, and then along with some set of inputs, these would go into your ZK circuit. Now, Jeremy's going to talk a lot about how this actually works, but the ZK RISC-V chip also has access to traditional read-write memory system, some number of syscalls, as well as some number of acceleration circuits. In this case, the one referenced up there is a SHA-256 accelerator circuit, which Jeremy can talk a bit more about if people are interested in.
Syscalls is just, it doesn't support file systems and things like that.
Not yet.
But we actually have an interesting mechanism. So currently we mostly support sort of a couple of streams of input and output to talk to basically the guest machine. Those are. I'll go into that.
I'll say for the recording purposes, Jeremy can talk about that a bit more when he's up. But Dan was asking if it actually supports syscalls, and or maybe I'm supposed to say Dr. Bonet. Sorry, I don't want to like. And the answer is yes, there is a way to expose syscalls to the ZK guest.
And actually, we're eventually going to have full libc support.
Yes. Yeah, we actually do have, yes, right now we support a subset of Pico libc. So actually the soft flow emulation and a bunch of other things. So you can, in theory, just port physics engines and or generative art engines and maybe interesting things like that to the system. So notably, this is the first, and I'm always hesitant to say first, but as far as I'm aware, this is the first Stark-based ZK proving system and verification system that is actually licensed under a free and open source model. So it's available now under the Apache 2 license at this GitHub URL. There is a working example of integrating this with a blockchain. So we have our verifier ported to, I mean, any WASM chain really, but we did an example on top of Near. And that's this battleship game. So it's a ZK battleship game where the state lives entirely on the two people's individual laptops. And then the state transitions and commitments to your internal state end up on chain. There's also this example of a new signature scheme. I think the Cairo people also wrote about a similar thing. Tim, who will be talking later, did these examples. And then we also have an example of a ZK voting machine that lets you verify that your vote was included in a tally, but not otherwise reveal any other information about how you voted or any of that. And then we will be working on some financial examples as well as other examples in the future. I do want to talk about some of the use cases for this. You can see the slide's not entirely done yet. So Battleship is obviously an example of doing ZK gaming. Gaming is very interesting because you can now have these sort of hidden information games, as well as, and this sort of goes to scaling distributed computation, but you can actually make like your players into servers, if you think about it, because if like computers, if nobody can lie about the outputs of their computation anymore, then you can have a computing environment where you actually let the client, so it's, generally speaking, you can trust the client now. So you can actually run game logic and like say EVE Online, you're all part of, you're in some galaxy or solar system, the people who are there can generally share some of the computational duties. So there's a chance to like reduce the barrier to entry for multi-party systems. Identity, very excited about ZK identity for a lot of reasons. It really enables very interesting pseudonymous cases that help you, I guess, I think about it as making identity scarce again. So yeah, so the idea, generally speaking, is that you can collect a bunch of key materia, own this in your wallet, and sort of mint a new personality for yourself that has some derived, like say you can make an open source credit score, for instance, that says, here's this algorithm that will take any number of these inputs, like, my phone, like a proven record, like a verified phone number or address history or bank account balances or crypto wallet balances. And you can have some model that takes these inputs in and produces some score. And then you can attest to, say, Reddit, when you're trying to create a new account, that this like SOC, I don't know what to name it, RISC-V. You can follow us on Twitter if you want somewhat amusing SOC. I could attest that that's associated with somebody with an identity score from this model of above 100. And moreover, you can also do some interesting things with limiting the number of accounts, like pseudonymous accounts that can reuse that same key materia. Jeremy, we'll be publishing some stuff about this. Generally speaking, when I think about the Near case, or like the Battleship demo, that's an example of doing off-chain computing and then attesting to it in a public environment. Now, the game logic for Battleship is not particularly complicated, but notably, what ends up on chain is information about a state transition and a proof that it's valid with respect to some program. Now, that program can be arbitrarily complex. The cost on chain of doing the verification is exactly the same, independent of the amount of computation that's going on off chain. And then through recursion, and we'll also be hopefully publishing, I don't know about publishing, but writing a lot more about this and possibly publishing some papers about how to use recursion and other properties of ZK systems to really scale various aspects of distributed systems. Beyond that, mission critical systems. So if you look at this is probably a bit farther down the road, but there are a lot of systems where you effectively have to put redundant systems into place, have them vote on the outcome because you're concerned about not necessarily malicious actors changing the output of a computation, unless you consider like, interstellar radiation a malicious actor or something, which, I don't know about that. Don't need to get into the three-body problem yet. And then obviously high-value targets such as voting machines. Now, what's really interesting about this, aside from the example on a web page that actually utilize ZK to ensure that information's hidden, this also lets you, if you think of a bill of materials in a traditional software system, you can actually understand that the code that you intended to run on a system is the code running on a system. So if you take a hash of all of your audited code and you have your bill of materials for what's supposed to be running in your SCIF or voting machine or whatever, you can actually produce proof with every single computation that the audited bits of your code are the bits that ran. And this has really broad implications for preventing like supply chain attacks.
There's a question here, which is, are there any curves or signature schemes that RISC-V won't support?
So the question is if there are any curves or signature schemes RISC-V won't support. I think Jeremy,
Yeah.
I think in general, let's Jeremy, we'll have you answer these questions when you're sitting here,
Yeah.
so you can end up on the recording. It's complicated, is what I'll say. Or Jeremy, I think you're up next anyway, so just come over here and talk.
Sure.
Yeah. So Jeremy can answer this question.
So generally our goal is to support as wide a range of use cases as possible. And so our goal is in many ways to try to make programming zero knowledge systems as easy as possible for ordinary programmers. And we also intend to, like we have the SHA-256 accelerator, add accelerators for other common cryptographic operations that would be too slow to run using the RISC-V processor directly. Although technically, you could technically run anything on the RISC-V processor, obviously, you get huge wins from putting direct support in a circuit for those accelerations. We intend longer term to support a generic mechanism for allowing additional circuits to be added and associated with custom instructions within the RISC-V ISA, because the RISC-V ISA has innate support for sort of custom instruction extensions. And to that extent, we are interested in supporting as wide a range of things as is possible. Certainly, some things will be easier, more difficult based on the finite fields that our proof systems ends up using and so on. But that said, as much as we can within reason. And hopefully we'll be getting community contributions from this as well. I should also mention, I don't know if we explicitly said it yet, but that all of this does currently already exist and is running. You can actually run these proofs right now. We fully support the RISC-V ISA and pass all the conformance tests by the RISC-V group. So, this what we're talking about here is not a thing we're building. It's a thing that we have built by and large. So I'm going to talk a little bit in detail about sort of how we actually implement effectively the actual RISC-V circuit, including particularly how we deal with RAM and how we emulate RAM within the proof system, as well as a little bit about sort of the structure of our proof system. Our arithmetization is more or less similar to AIR, but with some slight differences. So I'm going to cover a little bit of that as well. So I'm going to make the assumption sort of that most everyone is probably familiar at a high level with how STARKs work. So feel free to ask any questions. So the first thing I wanted to talk about is how we represent the program that the user passes us, the ELF, and the loading of that within the proof system, as well as sort of the overall structure from a time perspective to how the processor itself works. So the notion here is that we divide so STARKs are naturally sort of divided into cycles, and there's a repetitive sort of arithmetic circuit that relates each cycle to the previous cycle. Within the execution of a given program in our system, there's sort of this process by which initially there's a special initialization cycle that sort of resets the state. Then there's what we call the program load phase, wherein we're effectively loading the program data for the particular ELF into our emulated memory. And then we sort of do a reset, which jumps the program counter to the beginning of the execution. And then basically the actual processor it takes 3 cycles to execute each instruction, which is basically composed of instruction to code, and then a compute/load phase, and then a register update / write to memory phase. What's notable is that effectively we always have at most 1 memory transaction for each logical cycle, which is important to the way that we actually implement the memory system under the hood.
It might be helpful to say just at a very high level that your goal is to let someone write a C program.
That's right.
Compile it down to
RISC-V.
RISC-V.
Yes, yes,
And then just run the prover as is.
exactly. Yep,
So C to proof.
that's right. Exactly.
That's what the system actually does.
Yep. Yep. Yeah, and so that is so I think one of the great things about this is that by using this sort of mechanism, we then look like a normal computer to people, and people can reuse existing software. We're reusing a huge amount of the existing tool chain in terms of compilers and language support. And I'll also get into a little bit about the way in which we do the interactions between the system running inside the proof system and the outside world, because that's obviously an important how you talk to the Oracle and so on.
I should have mentioned this also, Jeremy. You mentioned that on our website, not in GitHub, there's like a full write-up of how the battleship example works.
Yep.
Which sort of is like, if you want to go home and read more about this will sort of reinforce your reading of that particular explainer.
All right. So one of the things that's notable is that so in your Stark, there's typically a set of columns which represent sort of like a hardware register, if you will, over time. Every given cycle, that each of those columns has a value. We actually divide the set of columns that we use into 3 distinct groups of columns, and each group of columns actually is put into a separate Merkle tree. So the first set of columns are actually what we call the code columns. And those columns represent public data that is known to both the prover and the verifier. And this is actually where we encode both the control sort of flags that say, okay, well, this is the initialization cycle, these are the load cycles, these are the sort of 3 cycle structure of the execution, as well as where we put the actual ELF data that's to be loaded. And so by doing that, we're basically able to put all of our sort of control logic into that set of columns, and that's part of the Merkle tree that is checked in the proof system, similar to the main data Merkle tree, but because they have different Merkle roots, we do have to. As a result, we end up having to prove 2 Merkle paths instead of 1 when we're doing the verification. But what that allows us is to fit a huge amount of constant data in and make the proof system be able to make use of all of that, which is important. So that otherwise we'd have to say, for example, prove that our code hashes to some value, which would be much more expensive, right? So that's kind of a good trick there.
Maybe a related question on the chat.
Yes.
Do you also implement control and status registers?
So interestingly, the RISC-V, the control of status registers within the RISC-V architecture. Yeah. So currently we don't. Although we are going to add support for the, because we only operate in user mode effectively, and the normal mechanisms by which one calls into the system modes, we actually just implement as that's what induces the termination of the program. That's like effectively the halt instruction. In our next version of the circuit, we do intend to support the CSR registers, including the standard sort of timer registers, as well as so we don't intend to support the full the system mode, but we also do intend to use the normal system call mechanism to do our interactions with the external world. Currently, we use this memory mapping trick to do our interactions with the external world.
Another follow-up question on this: is the program by default a public input?
Yes. So the program is by default a public input. Now, technically, the only thing you need to do the verification is the Merkle root of the control set of columns. So in theory, one could, for example, pad your program with a bunch of extra random bytes and then generate the appropriate Merkle root. But certainly the prover needs to know the program, and the verifier needs to know the hash of the program's sort of control traces in order to do verification. So you could technically verify a program that you don't know what the program is. Typically, none of our use cases do we make use of that back.
All right, although I will add just briefly that you can imagine use cases
Oh,
where,
yeah.
where some say, governmental or otherwise trusted body audits a bit of code and attests to some bit of code having certain properties and says this code that has this hash has these properties, and then people could run it, prove that the results come from this bit of code.
Yeah.
Without necessarily ever revealing the code, but that's like I don't know, future use case,
Yes.
let's say.
So then the next set of sort of columns represent the sort of standard, columns you'd have in any sort of a Stark, and they hold the state of the RISC-V during execution, and they also hold the information necessary to do the memory transactions as well as the memory verification, which I'll get to in a bit. And then we basically have the effectively accumulation set of columns, which basically hold products for the Plonk, permutation verification mechanism. So we use basically a Plonk style way to prove a permutation, which is used as part of the memory consistency evaluation.
Actually, is
Yep,
there
go ahead.
anything in the RISC-V instruction set that's not supported in the control side?
No, so currently we fully passed the RISC-V compliance test for the R32 VM or IM. Yes, thank you. Aside from for the user space set of instructions, we fully support them all. Some of them are no ops, like for example, the memory fence doesn't do anything, right? But it does,
Oh.
yeah. Yes. But yeah, generally you can literally compile down random C code, and you can actually even use floating point because we actually support a very basic version of picolibc. I can write a bunch of floating point code and it'll get converted into soft float and put into the system. We actually are seriously considering in the next version of the circuit adding the proper floating point extensions because with lookup now, I think that the actual FP unit, while an annoyingly complex engineering task in terms of the total size expansion for the circuit isn't super huge. And one of the nice things is because the circuit definition itself is part of the verifier and the prover, we can actually have different versions of the circuit. So we could, for example, have optional floating point support. So if you want to use a lot of floating point, you pay for a bigger circuit, but then your floating point is much cheaper. If you don't have much floating point, you can use the smaller circuit that doesn't have the FP support. That's part of the reason. So largely RISC-V as the architecture was it was sort of lucky. It's just a very nice modern architecture. It's modular. It's really built for having the minimal set be implementable on a tiny amount of digital logic, which means that it's also implementable in a tiny amount of arithmetic circuits. It's not like the most perfect architecture for ZK, but it's actually pretty reasonable. So
I actually have a question now, Jeremy.
Yeah.
So this means what's the size of the RISC-V circuit relative to say SHA accelerator? If you don't care about recursion on blockchains, for instance, how much smaller does that circuit get?
I think that I don't have an exact number because I haven't actually measured that, but my guess off the top of my head is that the RISC-V circuit is probably about 60% of the circuit.
Oh wow, okay.
The SHA accelerator does take actually a fair amount of constraints because it's not trivial. Yeah. That's a very good point. We should really make that an optional.
Yeah.
We should optimize that. Genius. All right. I don't know why that never occurred to me. All right, so I wanted to talk now in detail about sort of the mechanism that we're using to do the memory validation. So as we mentioned earlier, we're effectively doing at most one memory transaction per execution cycle. And honestly, if we don't have a specific memory transaction, we just do a read of memory address 0 or whatever as a default. So there's always one memory transaction per cycle. So there are two sets of columns. They're both in the data section. One of them is the sort of memory operations, and those occur in program order. And so there's a sort of cycle of which logical cycle this is, and that just moves forward, monotonically, and there's a constraint that always moves forward monotonically. And then there's basically the address, the data, and a read-write flag, which of course have constraints that are hooked into the rest of the circuit. So that basically,
Just real quick, Jeremy,
Yep.
if you do,
I can do this.
if you do
Yes.
this, you can like,
Oh,
you
yeah,
can
there you
kind of
go.
do a pointer thing that everybody will see, and hopefully
There we go. Yeah. So this is the cycle. This is the normal ordered. So this is all happens in cycle order. And so what we're saying here is, okay, at time 0, I'm going to do a write to address 3 of the value 17. And then at time 1, I'm going to do a write at the address 7 of the value 3. Then of course, later I'm going to read from address 3, and I'm going to read back 17, or at least I should, assuming memory is valid, right? So what happens is during the initial program execution, we generate these columns, and we just model memory externally, right? Then what we do is after execution, we do a sort of all of the values in here into this sort of verifiers, this sort of second copy of the memory transactions. But these are, instead of being sorted by cycle, are sorted by address first and cycle second in lexicographic sort order. What that means is that all of the memory transactions that occur on the same address are all now located next to each other, and all of them are in proper cycle order. At which point, basically, it's possible to quickly verify the validity of the memory transactions. Oh, wait, you know what? This should actually be a 1, shouldn't it? Yes. Oh, shoot. I guess I can't edit this document while I'm doing this. Sorry. This is a 1.
I need to remember that.
This is a 1 right here. Yes. So what you see is we write 17, and then we read it twice, and then here we write 2 different values and read it. And interestingly, the requirements for the verifier are basically written here. They're actually fairly simple. If the addresses are the same, then we have to verify that the cycle is moving forward, and if it's not a write, we have to make sure that it matches whatever the previous value was, and then also that if the otherwise, if they're switching between addresses, the only thing we care about is the addresses are going up. You will note, by the way, that this allows an initial read prior to a write to return any value whatsoever, which we actually take advantage of. Basically reads of values never written are in fact undefined, and we use that actually as a way to interact with the external world. So basically, in addition to so besides the set of constraints that represent the verification of the resorted versions of the address, we also have to prove, of course, that these 2 different tables are in fact permutations of each other, which we do using the sort of Plonk permutation argument, where we basically commit to the entire state of the data trace Merkle tree, and we use that and the Fiat-Schmier sort of mechanism to then pick a number, a set of ways of. I won't go through the Plonk argument in detail. I'm sure people have read the paper, and if not, it's a great paper. At any rate,
There is a question
yep.
on the chat. How do you efficiently check the inequality?
If we don't efficiently check the inequality, what we do is we subtract, and then we bit decompose so if we want to prove that A is greater than B, or greater than equal, we'll say, we take A, we subtract B, and then we bit decompose it and prove that it is a 20-bit number. And so since our field is like 31 odd bits, if they're the wrong way, then it's not a 20-bit number, and so it fails the constraint check. Now, we're going to replace that with lookup, which will allow us to very rapidly do that with a much smaller number of columns and a much smaller number of constraints. But right now, we actually spend like 20 columns for the bit decomposition of the subtractant. And we actually reuse interestingly, we use the same set of columns for these 2 different cases because they're never simultaneously true, right? So there is a fair amount of, given that we already are using, Plonk for memory verification, you would think that the idea of lookup would have been self-evident to us when we were writing this the first time, but it was not, unfortunately. So we're building a new version of the circuit for that. Cool. All right, next slide here. So I want to talk a little bit about how we do the interaction between the actual ZKVM, which we call the guest in sort of standard, virtual machine kind of terms, and the sort of prover, which is the host from a sort of a formal term. So let's say we want to have the guest send something to the host. Well, the guest just writes to an address that is a particular well-known address, And the host is like, oh yeah, I see you right there, right? Because obviously it's just running an emulation. The host can see the whole world, so trivial. On the other hand, if we want to get something from the host to the guest, then the guest reads, there's a region of memory that we set aside for host to guest communications, and we keep the guest keeps track of a pointer, and it keeps bumping that pointer and reading the next address. And as it reads those addresses, since those addresses have never been written to before, they're uninitialized, any value is allowed to be returned. And so right when that address is read, at that moment, the host will decide what it would like the guest to read and places that in there. We use this to basically generate what is effectively a sort of a private two-way stream, which we actually, currently we have sort of our own sort of read and write calls, but we're actually going to move that to actually inside of libc, so that they'll actually be like real like things that look like file descriptors that you can read and write to like talk to the host or the guest, and things like that. And then we're going to also implement a number of other sort of systems on top of that. Well, I probably won't go into detail that, but if anyone's interested in how you can build like something that looks like a file system inside of a zero knowledge proof system, we do actually have a plan for that even. So I don't think, do I talk about, I didn't, no, I didn't.
Skip the slide.
Yeah, this is booth.
So.
I think that's it. The only other thing I wanted to mention is, it's not explicitly written here, but I think it's one interesting note on the model is that the other sort of interaction between the proof system and the outside world is this thing we call the journal. So basically there's another region of memory that the guest writes to, and at the termination of the guest from the normal execution, we go into the SHA accelerator circuit where we SHA up that region, and that ends up coming onto the output of the proof. So effectively the basically if you want to talk privately to the host, you can read and write to these sort of logical streams. And then there's also this other region that you can write things you want to be publicly known. And then those get basically emitted, and those become part of the public record. So when you provide a proof, you're basically showing what is the journal, what did this thing write to the journal, what is the code that this thing is running, and then a bunch of sort of opaque cryptographic goo that basically allows you to verify the correctness of that. So here, yeah. Cool.
Are there more questions right now? Otherwise, Tim is going to talk about formal verification.
Actually, so one thing that's not written is normally when you write for a zero knowledge prover, you don't do computations. You provide witnesses that things were done correctly. So you're writing a verifier. So for example, if your C code, like in your battleship game,
yep.
Maybe there's battleship game is not the greatest example, but imagine you do the sorting algorithm. You would never implement the sorting algorithm inside of the circuit. You would
right.
just sort outside,
yes.
and provide proof.
Yes. So
how is that
we use
here?
what the way we do that is that if you wanted to, for example, we're just talking about trying to get a compiler to fit inside of the zero knowledge system. And like one of the examples that comes up is, well, register allocations are very expensive and complicated, but verifying a register allocation is actually a lot cheaper, right? So you can use this sort of non-determinism mechanism in any of these things. And the way that works in terms of how we implement that within the ZKVM is that inside the guest code, inside the ZKVM will write to the host saying, hey, I would like you to solve this problem. And at that point, by the way, the host can just read in any location in memory just to see whatever it needs to see. And then the host will write back the result, which the guest will read. And then the guest will verify whatever it is, right? So what we're still in the process of building a sort of a set of like wrappers. Like, for example, we've been considering in Rust having a macro mechanism where you can say, like, you can basically decorate that this method is meant to run on the host, and then sort of kind of do all of the back and forth between the host and the guest, so that you can basically say, okay, well, I want this is what I want to run, and this is how I want to verify the thing I ran, right? And so you can basically do these sort of blocks where you're like allow you to do that acceleration kind of technique.
I guess you could then like implement parts of like the C++ standard library too.
Yes.
If you wanted to, and have various sorting algorithms or whatever.
Yes, exactly. You could do yesterday sort, and then you say, okay, here I'm going to call sort. The actual host or the guest is going. Host is going to do the sorting. The guest is then going to place that back into your memory, and then you're going to do a quick walk through it to verify.
Although I guess, sorry,
Yes.
probably not relevant to this, but we just use file descriptors eventually, right? You write all of your list you want to sort into a file, and then
You could do that, yeah, absolutely. So there's all kinds of ways to do that. Our fundamental interest is figuring out how to get as many of these metaphors to be as easy for developers to use, right? So and so currently, we don't really do a lot of these, like the battleship game, for example. We just, like, the way it works is that you read in where the user wants to place their ships, and then we just verify that placement of ships doesn't have any ships overlapping. It has all the ships, none of them go off the edge of the board, and then we basically and if any of those things are the case, there's sort of an abort that we define an illegal instruction will make it impossible to produce a proof, because if you execute an illegal instruction, the circuit will fail, and so then it's impossible. So what we basically do is we basically say, oh, well, if you have a bad board state, then abort, otherwise terminate normally, and then basically you have a proof now that the user has committed to where to place their ships, and then we basically, we write to the journal the hash of that ship placement plus a hidden secret, so that you can't do hash inversion on it. And I guess Bob's your uncle, right? So yeah.
The other question I had, sorry, I'll just so I think I asked you on the way here, like, so why choose the RISC architecture? Or, for example, RISC has all these registers, which you couldn't care less about. You don't need registers here.
True.
So why not rip that all out and kind of define your own?
Yeah. So the question is why pick an existing ISA as opposed to basically building a ZK specific new ISA? And honestly, the answer to that is some back of the envelope shows we probably only are losing like 2 or 3x performance by using something that already exists, and now all of our tool chain is already done. So it's primarily a time to market thing and an ease of understanding for existing programmers. Like right this second, I now have a huge library of Rust code that already compiles and works in this system, right? No one needs to port any code. No one needs to build a new compiler backend. All that's done. Now, at some point, will we, maybe it would make sense for us to build an LLVM backend that supports a new architecture that is specifically optimized for zero knowledge proof systems, and then implement that architecture and implement the LLVM lowerings. But there's a lot more engineering to do for that. And at the end of the day, what's cool is that if we are using something that's a normal architecture like RISC-V, and people thus program in normal languages like Rust and C++, if we do end up switching to another architecture, it's, most of that code should port across effectively. And to be honest, I do think the total cost of using RISC-V is actually not particularly huge, and it's a big accelerant in terms of time to market.
Yeah, you can also mention the existing battery of tests.
Oh yeah, that's another huge thing, right?
And the tool chain and the extension mechanisms and all these things are like well supported throughout the tool chain. So
yes. And actually, there's
quite large accelerator market.
There's a formal description of what it means to be RISC-V, so we can actually formally verify that our ISA.
Which is a perfect segue to
yes.
3 more questions on the chat.
Sure.
The first one: can you share any tricks you use to implement SHA-256?
Oh yes.
We need to do a write up on that.
We actually, yes, I've heard this question enough that I do think we should do a write up. The short version is that if you look at the state of SHA-256, there's sort of a set of registers that there's 8 of them, and most of them are sort of like shifting back every cycle, and then 2 new elements are created. If you unroll that in time so that you place effectively 2 elements, you make 2 new elements every time, and then you read back some number of cycles. So the one thing about Starks is they have this repetitive structure, but most of the time people only go back 1 cycle in Starks. But you can go back as many cycles as you want. And so if you unroll the SHA-256 in time, you actually only need to produce regenerate 2 new registers. So it doesn't take very many columns. And then we basically bit decompose them. So we basically take 96 columns, which gives us the 2 new registers, A and D, plus also there's this W register, which is related to itself. It's the and so basically you take those 96 bits, and then we can fit everything into rank 3 constraints. And you take 60 cycles or something, or 68 cycles to do a full SHA. one round, or not one round, one compression, one full compression.
The second question on the chat is, how do you compare to tiny RAM?
So largely the idea of use of von Neumann architecture using sort of zero knowledge proof systems that TinyRAM does is very similar. The primary differences are that we are implementing an existing ISA as opposed to some new ISA, and then also the way in which the permutation validation was done on that was a Benes network or Benes network. How do you say that? Benes, yeah. Whereas in this case we're using the Plonk. So there's the Plonk mechanism for verifying the permutation is massively more efficient in terms of prover time as well as verification complexity. So, but at the heart, the conceptual notion of verifying RAM via permutation is similar.
And there's the last question on the chat. Is there any limitation on the recursion call depth?
No. It's just emulating a normal RISC-V processor. I mean, so there is, we only have 2 megs of RAM, so your stack can only get so big. And of course, also the finite field for the FFTs, there's a maximum number of cycles you can run within a single instantiation before you know, but effectively, no, we're not doing any tricks with control structures or anything. It's literally just random machine code. Like you can do indirect jumps, you can do, like, you can actually do self-modifying code if you wanted to. Now we actually, yeah, because it's read from RAM, right? So you read it through alpha into RAM, and then if it's in RAM, you can modify it. Now, technically, we actually have 2 different regions of memory. One which is write once, which is what we used for the program codes, so that we actually will segfault if you try to write to your own program code, because we think that the chances that someone wants to correctly use self-modifying code versus someone's being hacked by self-modifying code would probably err on the side of making it not writable. But in theory, one could in fact generate code in the data segment and then jump into it, and it would actually work the whole 9 yards. It's like a real von Neumann machine.
What was the biggest number of cycles that you can handle in a single proof?
The maximum, so our finite field is 15 times 2 to the 27 plus 1. And we do a 4x expansion. So that means we have 2 to the 25. So what, 32 million cycles? And there's 3 cycles per instruction, so about 10 million instructions is the maximum you can do in our current proof system. Now we're thinking. I think the next version of the circuit we're going to switch to using the so-called Goldilocks field, although that was also used for a previous field. But in this case, that represents the field 2 to the 64 minus 2 to the 32 plus 1. At which point we could do larger proofs because yeah. Yeah.
I think you mentioned something like SHAR accelerator. Is it a hardware accelerator?
No, it's just what I mean by that is it is a component of the arithmetic circuit that sits next to the arithmetic circuit that represents the stepping of the RISC-V. That is so when you do a SHA-256, there's basically some weird dance you can do where you sort of execute certain instructions and poke certain memories that like basically induces the machine to verify a SHA inside the circuit. But it's not, none of our stuff involves any hardware acceleration in real hardware. It's all the imaginary sort of.
It's like you're making a, it's like just like any standard like microcontroller, like microprocessor these days has like who knows how many functional units like actually on the die. This is basically a mechanism to make new functional units on your arithmetic die and then call them like you would in a in your standard gigantic Intel chip or something.
And notably right now all of our stuff runs on CPU multi-threaded in terms of the open source implementations. We do have commercial non-open source implementations that are GPU accelerated that make the proof system significantly faster using GPU acceleration, but otherwise everything else we've got is open source Apache 2 licensed.
10 million cycles was for GPU or for
1 million cycles was per second was for that was for GPU. Yeah, it's about 30,000 for CPU.
Of the VM.
Yes.
This number of cycles is constant. It's 10 million because of the finite field.
Yes.
The speed of the emulated circuit is 10 megahertz or 1 megahertz on a GPU or like 30 kilohertz.
Just in terms of running time. So if I do have a program that runs for 10 million cycles,
how
long does it take to generate?
Like on the order of 20 seconds, I guess. Was that right? No. Well, it depends upon. Yeah, it's about right. Yeah.
So fast or slow?
That's pretty good.
Yeah.
Yeah.
Yeah. Want to make sure Tim has time to.
Yep,
go through
let's
stuff.
do it.
One more question from the chat.
Okay.
Doesn't the Plonk argument depend on being defined over a very large field, much larger than the degree of
So,
the polynomial represented?
Correct.
in the case?
And what we do is we use for the Plonk argument for the so we use a small field for the most of the circuit, but then when we do the deep alley component of the Stark proof, as well as for Plonk, as well as for the Fry, we use an extension, a field extension. In our case, because we're using a 32-bit field, we use an extension, a field extension of 4, and we're basically targeting about 100 bits of security in our current implementation. Cool.
Thought we had an hour overall.
Told you there'd be lots of questions.
Ah,
I
here you go, Tim. There you
go.
You're it's set up.
Fantastic.
Oh no, I don't want to share it. I want to slideshow
we don't
it.
need to hit that
Okay.
button.
Yeah,
Yeah,
there
sure.
you go.
Yeah.
You gotta sit down so people can see you. Or
I
I
have
gotta
to
point, or I
sit-
can point this at you if you want to stand
No,
up.
it's good. It's good. It's good. I'm gonna do the thing. So, hello, internet. All right. So just for the folks here in the room, I don't know how popular formal methods are in California.
They're appreciated.
So are they appreciated? If I say things like lean, is this a word that anyone's heard? LEAN? I'm not seeing any signs. Oh, only one. Oh. So I don't use that system, so I was actually very excited that nobody knew what it is. Est-ce que vous parlez-vous français? If I say the word cock, you know I'm talking about roosters?
Yes.
Great. All right, we're going to skip all that then. All right, so I'm going to go ahead and talk about the work that we are doing at RISC-V on what I'm calling the product of zero knowledge in the Stark sense, and formal methods. This will be a quick one. Feel free to interrupt. All right, so at a very, very high level, we are using zero knowledge to prove that the computer ran the right program, which is great. We're also using formal methods to prove that the program did the right thing, which makes us better than everyone else. And when you put the two together, you get a theorem that means that the computer did the right thing, which so far as I know is a novel claim in the industry. All right, what do I mean? Let's peel it back. So you're going to see a number of ways in which FM and ZK are going to interact here, and I'm going to go ahead and get started with the most important ones. So we are currently using formal methods in the cock-proof assistant to prove that our ZK Stark tools work as advertised, right? Everything from how do you multiply polynomials up to what is the RISC-V ISA, what is the RV32IM ISA, all the things in between. You know, what is a hash function? What is a deterministic random bit generator? What is a Faustian heuristic? What is the number theoretic transform? What is all the other things that, I don't know, there's a lot of grad students in the room that you all have been studying for some time, I assume. So we're going to go ahead and prove that the thing does what it's supposed to do. But what I'm really excited about is that all of our formal methods proofs are going to be compatible with the existing RISC-V formal methods ecosystem. This is a novel feature of RISC-V. RISC-V is a processor that's been formally specified, and the committee has ratified a formal specification. And so that's what we're going to work off of. Because we're working off of that, we are compatible with all of the other things out there that are also working off of that, which are all a bunch of formal methods tools. I'll mention some of them. I'll note, by the way, that Cairo doesn't have any of that. nor would any other thing that asks you to write your own circuits. All right, and what's the big deal about that? Well, I don't know much about the blockchain, but I understand that it's kind of an adversarial regime where maybe it's a good idea to have some level of confidence other than the intern worked really hard last night to believe that it's all good.
Or $5 billion bug bounties.
Hey, whatever's clever, right? So the important thing is that if I do my job correctly, it will be possible for users entirely with open source tooling to be able to build end-to-end applications where not only are the tools running inside the VM proven, but also the tools that are making calls into that and depending on that, they can also have proofs. We'll be able to enable proven architectures of actual application suites, not just tiny little useless components. Right? So why don't I make some bold claims about the things that I want to be able to share with you in a year or 10 years, however long it takes. All right, 4 statements, and I'm interested in feedback on all of them. I seek to prove the following: completeness. Our verifier accepts every valid receipt. This is not a super important property to me technically, except that it just means that the verifier is not trivial. It means the verifier doesn't just reject everything, right? Soundness. This will be a fun proof. Our verifier rejects invalid receipts with high probability that we'll bound using the latest proven bounds in Reed-Solomon proximity gaps, for example. Uniqueness. Here's a property that very few specs bother to prove, but it's actually, I would say, very important in a distributed regime. Our verifier is uniquely determined as a mathematical function, not as an algorithm. As a mathematical function, our verifier is uniquely determined by its specification. If I produce a verifier and I prove that it satisfies public spec and you also do, we don't have to compare the code. If they both satisfy the spec as functions, they're going to agree on all inputs, which means that we have a well-defined notion of what it means to verify a proof. It's a crazy thought. I don't know if anyone else has that. And then lastly, compatibility. Our verifier, the polynomial constraints that we cooked in, characterize specifically the RV32 IM instruction set architecture, which again is well defined and formally ratified in all this, including our host to guest memory mapped IO model and platform extensions, all of which are also ISA compliant in our approach. And it's this last thing that allows you to take our proofs and apply other formal methods, tools, and actually get sound theorems out, right? Like, if I didn't need that, then it wouldn't really be important that it's RISC-V, right? You just be whatever Tim says it is.
This is composability property?
Yeah.
Compose with spec.
So this here will be that. Okay, so let me give some examples of what this compatibility will get, right? So when I say that we are exactly RV32IM, when I say that, if you come to me and you have a proof and you've proven that some binary like ELF file is an RV32IM program that computes, I don't know, whatever, Fibonacci, then your theorem will hold inside a virtual machine. That's what that means.
By the way, there's another property that's often needed, which is this non-malleability property. But given one, receipts are proofs, right?
Yeah.
Yeah,
Yes.
So given one receipt for a particular statement, you can't produce another receipt.
Hey, that seems like a good property to have. Yeah, I'm gonna add that to my list. This is already useful.
Yeah, in fact,
I'm at the start of this
somebody-
version.
We got into like a 3-hour-long conversation about that exact property because people were certain that the system didn't have that property. We just agreed with them, but it'd be great to prove it.
Wouldn't it though? Yeah, so the intent here, and again, I'm interested in the feedback, right? We're at the start of this journey. This isn't me showing the paper. This is me promising to write it, right? At the end of this journey, my intent is that we'll have a platform that there's some reason that you can actually trust it with things that matter to you other than, you know, that you're impressed by my nice sweater or whatever other criterion we use to decide what operating systems to use and such. All right. I need to pick up the pace a little bit. So why? Why are we investing in all of this? Here are the things that I'm hoping to get out of this experience. One, a precise description of our security model. Call me crazy, but when I say that we apply Fiat-Shamir, I'd like to have something that like describes what I mean and is rigorously attached to the actual implementation. So it's not just some hocus pocus that person can stay in a nice talk. What else am I going to get? Well, a natural byproduct of all of this is that I'm going to wind up with an interactive textbook that explains our system from the ground up, including this entire set of curricula that is necessary in order to actually build the thing. Now, when I say textbook, I don't teach. I'm not going to put problem sets in there. My examples are not going to be like super inspiring, right? But technically, every single definition and lemma, together with proofs that you can step through in the proof assistant, will be in there, right? What else am I going to get? Here's the part I'm really excited about. A formally verified verifier compiled by a formally verified toolchain. All right, this does not exist in market, to my knowledge anyway. And in fact, this is a thing that could only be done in the Coq proof assistant. Why is that? Well, I need a formally verified toolchain, and I only know of one of them, right? The CompCert, wherever it is, the CompCert C compiler from INRIA, legendary genius Avialois project, which allows me to go from C down to my choice of x86, ARM, RISC-V, PowerPC, and half dozen other processors that Airbus uses. Who's paying for it, right? So that gets me from C99-ish, C99 Lite, down to these things. But we also have this brand new thing, my Zoe and Mathieu and a few of my other collaborators, called Certicoq, which allows you to feed in functional software written in Galena, the functional term language of the Coq language, and obtain C99 code, which has been formally proven by the compiler maintainers, which is my colleagues, to actually preserve the semantics of your functional program. Of course, this does require that you have a formally verified garbage collector, which we do. It has to be written in C, and it is, and it's fine. So in any case, I'm going to write this formally verified verifier. I'm going to write a functional program in Galena and prove it's correct in Conc using all these other things. And when I'm done, I'm going to big red button, and it's going to emit a bunch of C99. And then I'm going to hit the 3 big red buttons, and I'm going to give you a Linux binary, a Windows binary, and a Mac binary. And there is a proof you can take to the bank that they all agree on all inputs and that they exactly recognize the proofs or the receipts from our system. This will be probably the most reliable and robust piece of software you've ever run on your computer, unless you've used boring SSL, which is also has parts that are built this way. All right. And then lastly, compatibility with the existing RISC-V formal methods ecosystem, which is, I'll be honest, kind of a young ecosystem, but it does contain verifiable C, which gives me the ability to prove statements in higher order logic about the behavior of C99 software. We already use this with a garbage collector. It's verified in. Also, of course, gives us the sort of compiler, and its type checker, by the way. Gives us CompCert. It also gives us this project out of MIT called Bedrock, which is a domain-specific language for writing correct software and generating correct assembly from it. And they've written database engines in this thing and all kinds of other stuff. And then it'll also get us the SAIL RISC-V model out of the UK if they ever decide to start maintaining it again.
And what's cool is because some of these things, can be compiled in a provably correct way down to RISC-V, you can then run them inside the ZKVM too, so you can use it to
And it ain't no big deal. And in fact, technically, because of what Jeremy said, this entire stack is, we're going to be doing it open source because I'm radical like that. But it's actually going to be compatible with closed source applications too, because the Coq type checker can run on RISC-V, which means it can run inside our virtual machine, which means we can provide a proof that we checked the proofs without revealing the proof.
Unless you prove that private code does.
So I can have
this
a
binary, it implements this thing correctly, and no, we're not going to give you the source, but you can be 100% sure this binary is right.
Yeah, and it's been formally verified. So the interaction here, the zero knowledge component and the way that it interacts with the formal methods part, it's very interesting. There's a lot of ways for the snake to eat its own tail on this, and they all produce useful products. I swear. All right, how are we going to do it? So a few of my friends on the East Coast would laugh at the ambition of the statements on the previous slides, and they would say, how on earth are you going to achieve all of this? The crypto community has produced various formally verified implementations of very simple things, your elliptic curve, ECDSA kind of things and stuff like that. But there isn't really a gigantic corpus of peer-reviewed cryptographic models in these environments yet. So we're going to produce some of that. But broad picture, big picture, I'm going to do this the same way that we do everything else. I'm going to get a basic prototype up and running, checked with some test vectors. At that point, my functional program is just as good as everything Google ships. And then I will iteratively pick a worthy target, something that seems sketchy, fill in the proof until I'm convinced that the only things left are, trivial exercises for the reader. Then my interns will fill in those trivial exercises and the proof checker will tell me if they did their job right. We'll simplify and we'll iterate, right? This is basically the program. We're going to be doing it with a whole bunch of standard libraries. Adam Chapolo's group at MIT does a lovely job publishing a RISC-V semantic. Their semantic is not just a spec, but it also has a silicon implementation that's proven to be consistent with that spec. So it's all open source. It's a fantastic spec to work off of. We also have the MathComp library, which implements a ton of abstract algebra. Now, I'm pretty sure everyone here knows how to build a prime field. But by using the one from the standard library, third parties can be convinced that I didn't come up with a different notion of what a prime field is than the standard textbook one, right? So this anchors us down in our algebra. And then lastly, we depend on SHA-2. Well, NIST was not kind enough to provide a Coq model of SHA-2. However, this team at Princeton produced a proof that at least some specific version of OpenSL correctly implements HMAC on top of SHA-256, which means that they have a functional model written in Coq of SHA-2 and a proof that that model agrees input for input with anything that you get out of OpenSSL. And for me, that's good enough to say that it's probably the right SHA-2. And then lastly, a whole bunch of standard tools, the Coq Proof Assistant. There's this interactive doc generator called All Electron that I like to promote. It also supports Lean if you're a Lean person. Of course, the SerDeCoq compiler, which I'm a contributor on. It's awesome. It's the most advanced functional compiler on Earth, maybe. The CompCert compiler, which I think is probably one of the best pieces of computer science produced in my lifetime. And then, of course, everything from GitHub. Won't this take forever? Yes, yes, it will. Yes. I put this slide in here just so that I can tell my partners, hey, you said it was okay to say it would take forever. All right. It will take forever. It'll take a lot of time to fill in the blanks. So we're going to go and prioritize the scariest parts first and come back on everything else later. Even when it's done, it's going to have to be maintained, because who cares if the last version had a proof, right? You need the current available version to be proven. So this is a commitment right here. You're looking at these guys promising to keep funding me. And that is totally okay, right? That's totally okay. We've made it as far as we can't have with spaceships and airplanes and everything else on the back of academic papers, which I contend have way more blanks than a formal proof that has a few things skipped. And of course, we're in a business that absolutely depends on precision, or so I would contend. And then what's going to be the impact? For our users, the ability to build and prove applications that depend on the idea that the computer did the right thing. For scientists and engineers on side my company, I'm basically the lawyer who tells them when you're stepping outside of bounds or when I can justify what you're doing, right? If I don't know how to formally verify what you're doing, it's probably not going to ship. For the formal methods community, of course, we're going to be investing additionally into the support for the RISC-V ecosystem, all the other tools that I mentioned. And then lastly, for the ZK community, we are hoping to deliver the highest standard and rigor of how our system works, why you should trust it, what our security assumptions are, and so on and so forth. So a whole lot of promises. This was the easiest talk I've ever delivered. All right, so there we go. Zero knowledge and formal methods. The computer did the right thing. Thank you.
So actually, usually these formally verified systems, they come with a performance penalty.
Yeah, they normally would.
What would the performance penalty?
Yeah, no, that's a huge deal. That's a huge deal. So right here, I talk about doing a formally verified verifier, which is going to be written in the functional Coq language, right? And a very natural question is, how on earth is that going to compete for performance against the kind of Rust that a 25-year software veteran like Jeremy can produce? And the answer, of course, is that, you know, the first version won't, right? The first version over here is going to be this entire functional thing that's symbolically doing multiplication to do finite field arithmetic, and it's not going to be wire speed in the first version. However, because it's written in Coq, because we are using the Certicoq compiler, because the Certicoq compiler was very wisely designed by my colleagues Zoe and Andrew and Mechu and others, this compiler has the ability for me to make calls to C functions from Coq, which normally would be like, well, how are you going to prove any of that? Well, that entire interface is formally compatible with CompCert and verifiable C and our garbage collector. So we actually possess the ability, this is the work mostly of the research group at Princeton, we possess the ability to write functional programs in Coq. Its performance is just kind of average, and then we will perf benchmark it and replace with calls to formally verified C in all the right places, which will converge on essentially the same speed you'd get out of your C program.
And notably, let's say that you're using this for some blockchain application and you've got recursion working, right? So what's interesting is if you have a formally verified version of the verifier and you run it, then it doesn't matter whether you trust the prover at all, because the whole point of the verifier is to verify that the prover did the right thing.
Bingo.
So the prover can be written in whatever. And once you start using recursion, then you can prove the verification inside the ZKVM and do that a bunch of times. At the end, you only really need to run the verifier once, right? So like by having one really indestructively correct verifier, well, actually, it would be nice if you could formally verify the verifier that's used in the recursion, which of course also a little bit expensive, but yes. Sorry.
Yeah. No, that's exactly right. Yeah.
Very cool. Two questions from the chat.
Yeah.
One, is there a limitation to the binary size?
Good question. So the chat asks if there's a limitation to the binary size. This procedure does not really impose any additional limitations. The virtual machine, of course, has limitations on how much memory it provides to you to do execution, and so, you know, we would inherit that. But
just for the RISC-0 VM, the limitation on binary size is simply the number of instructions to load it, right?
That's right.
Yeah. So it has to be smaller than whatever for like 40 megabytes or something, right? Yeah, I guess.
yeah. So here, though, I would say that when you're applying these methods, though, the main thing that gets you isn't so much size as how much time it would take to explain why everything works, right? You know, if you ever lectured, you understand that some things you can explain it in 5 minutes, and others you're making your course week notes 2 weeks in advance. So if your software is that like, oh man, I need 2 weeks of lectures that explain how this works, well, your proof is going to be like that too.
And then the second question is, Cairo has some lean proofs as well. Aside from describing an existing ISA with tooling, what specifically do these formal proofs achieve that the Cairo ones do not?
Great question. So I will let the Cairo folks, of course, like defend their own work, which is excellent, but I will say the following. So the most recent paper that I saw showed that Cairo has demonstrated that their choice of polynomials is consistent with their description of their ISA. They've done this in the lean proof assistant. I don't believe that they have a proof that their verifier is consistent with all of that. I think it's just the connection between the polynomials and the ISA specification itself.
Yeah, I don't think they're not proving currently the correctness of the start within the random oracle model or any of the sort of.
Yeah, I don't think they have any of the crypto math. And then additionally, so I'm also a user of the lean proof environment. I should mention I've been using it off and on since lean 2, which is a very long time. Lean, while it has excellent Bourbaki style pure math, has almost no computer science in comparison to the Coq environment. And so as a result, over here, the functional language Coq is called Galena. Galena is formally specified. There is no formal spec for Lean. Because Galena is formally specified, we were able to make a formal compiler from it down to C99, which has also been formally specified in Coq. Well, none of that's happened in Lean either. And then lastly, of course, INRIA has been working on the CompSert compiler since 2006, something like this. So the computer science situation in these two environments is extremely different, which I think is the main reason why the Cairo project winds up with the character that it has. Excellent paper, though. I mean, absolutely, they crushed the result. It really did, which is not a trivial thing when one considers that it's a bunch of proofs about polynomials interpolating correctly, instruction size. How would you do that proof?
Was there any reason they couldn't use Plonk? Were they forced to use Lean?
One of the co-authors is a Lean maintainer.
Oh.
So I assume that was relevant.
Wasn't like something about finite fields, isn't like something much easier Lean? I don't know.
So Lean has an excellent library for what I call Bourbaki style math. So this would be your algebra analysis topology, as most of us probably learned it in undergrad. I like their library very much. There's a mathematician who wants to do math proofs. However, they specifically do not have the goal of providing a library that's computationally useful. So for example, their model of polynomials by default is not computational, which might be shocking, but when you consider that they're very interested in real coefficients and equality of real numbers is not decidable, then suddenly it starts to become clear why maybe that. So we're right now in the position where, and there's similar situations happen in the math comp library in Coq. So for instance, we have our own implementation of all this arithmetic, and we've proven that it's a standard undergraduate assignment, right? Build me a finite field.
So I have a question.
Yeah.
Is this Bedrock language like a good smart contract language?
It's the most rigorous language. If it were to be used for that purpose, it would be the most well-defined rigorous language in that space, as far as I know. As far as I know. I'm not a smart contracts guy. I'm a foundations guy. Rock and roll.
Yeah.
All right. You've heard me make a whole lot of bold claims and even talk a little trash, and I've delivered no source code yet. So feel free to hold my feet to the fire on that.
Timing estimate, like how long? Like if you have a guess.
Incremental. So in terms of having an executable verifier by the end of summer, but with all the proofs, well, for that now, I mean, you understand how long it would take to write lecture notes on this many topics, and
Just depends on how many interns.
yeah, exactly.
And that
So
depends on where you're willing to be like, oh, I'm going to make an axiom that says that, the main theorem from the proximity gaps for Reed Solomon codes. I'm just going to say that the paper is sufficiently convincing. So here's an axiom for that. And then, you can always fill it later. But so, yeah.
yeah, so the early stages of this project, the real intent is to allow us to execute with confidence, which is not the same thing as being able to convince a skeptical third party that we did everything right. That comes towards the end of this project.
Although to some extent, like for just out of curious from your experience at Airbus and so forth, working with them, how much do they care that the turtles stop? I guess, is it okay to reference papers?
Yeah, that's a great question. So I'll now do the caveat emptor about formal methods. This is the stuff that they don't teach you. If I come to you and I say that I have formally proven some theorem, it doesn't matter which, I don't know, Birch and Swinnerton Dyer, right? Great. So I have a proof, it's in proc. I allege that it proves BSD. What are you going to do? Like if you want to convince yourself that I'm full of it or that I'm honest or whatever, what's your process going to be, right? Well, you can believe that the computer knows how to check proofs. We'll just assume that for now. But what else might go wrong, right? Well, maybe I stated the theorem incorrectly and proved the wrong theorem, right? Well, that's easy to do by accident, especially when you're talking about an entire software stack, because the statement of a theorem is not just the like 3 sentences in italics that appear in the Wikipedia. It's also what happens when you unfold every single definition that gets mentioned, right? And as you build a stack of an actual computer system, that gets deep. And so when eventually we present all or whatever fraction of this proof, whatever form it's in, the very first thing a skeptical person has to do is unfold all the definitions that come up in the main theorems, convince themselves that those definitions are what they were expecting, and then that the statement of the theorem is in fact the statement that matters. So this is already a non-trivial amount of work, even before we talk about how much of the proofs are done, right? If then I've proven 45% of the statements, leaving 55% unproven, well, now there's the additional task of that person going through and trying to convince himself that the stuff I didn't prove is all plausible, right? So even when the proofs are completely done, in my view, the effort required to review a formal development is still far greater than 0. And that marginally, if you skip a few, like the basic lemmas, like, hey, addition's commutative, I didn't prove it for the 5 times I had to do it, right? Like, this is probably not the make or break in terms of convincing someone of the proof.
Which I guess is another way of saying, like, with respect to the Cairo question, it's like formally verified is not necessarily the binary classifier that people often
it's not
use
so
it
good
as.
for that.
Yeah.
No.
But it is very valuable for like making sure that it's just reduces the set of types
Yeah.
of errors that can be made
Absolutely.
in software,
Yeah.
right? Like I think that like our goal is as much to convince ourselves that we didn't make a mistake as it is to convince external
The people,
parties
yeah.
that it's
Yeah, right. And so like a really great example from the recent stuff was so-called fiat Shamir bugs that Trail of Bits disclosed, which were really just people failing to commit to all the things they needed to commit to in order for the heuristic to work. So this is an example of something that would actually be really easy to catch in formal methods. Because the formal methods would notice the extra degrees of freedom, right?
Well, that have to be at like the whatever level their
But in order to be able to,
application is.
yeah, but well, and also in order to be able to catch it, to say what is a heuristic. So you're going to have to supply an interpretation there.